So the final part of understanding the formation of the solar system is getting rid of the debris. That is to say that we formed this selection of planets as well as asteroids and the Kuiper Belt by creating dust, which then agglomerates through accretion into boulders and planets, but there's still quite a lot of dust and gas hanging around, and we need to get rid of it. And this happens when the sun switches on, that is, it starts fusion, and it's suddenly making a lot more photons. And so we want to get rid of all this excess dust that's made, and we do it by something called radiation pressure. Now, this is basically the idea that light, despite being massless, has momentum. There are two different ways in which it works. So radiation pressure is direct, and the Poynting-Robertson effect actually also uses radiation pressure. But it's basically a very small pressure exerted by light as it hits the surface. And we're being pushed by light all the time. It's just that our masses are so big that that push is negligible. So we want to consider light to be a stream of particles, photons, that have momentum. And we can transfer, if you have a photon that is absorbed, then the momentum is also absorbed by the dust grain. So let's have a look at how this works. So you're going to have a radiation pressure is just force over area, and so we have a radiation pressure is the force due to the radiation divided by the area. Now force is the rate of change of momentum, so we have dp by dt over A. So this is basically saying the amount of momentum that is deposited by the light is what gives us the force. Now for light, even though it has no mass, we have this idea that it has momentum that is given by its energy divided by its speed. And so the speed of light, its energy, and remember energy is given by Planck's constant times the frequency, so we have h nu upon c. And so now we can differentiate that. C is constant, so it doesn't change, and so dp by dt is just dE by dt divided by c, and so now we can plug that into our previous equation, and so now we get the radiation pressure is given by the rate of change of energy divided by the area of cross-section of the grain and its and the speed of light. Now the energy per time per unit area is the flux. Now in this case I'm using phi instead of F because I'm using F here to be force. This flux is the same as the flux in the F equals sigma t to the 4. It's that flux. It is the energy per unit time per unit area, but we're using phi just to make sure that we don't get confused about forces versus fluxes. And so dE by dt over A, dE by dt over A is the energy per time per unit area, and so this reduces to just phi upon c. So the radiation pressure is the flux divided by the speed of light. And so we're actually going to rearrange this and think about it in terms of force, because what we want to do is exert a force on our dust grains. We've got a force due to radiation, which is the area of cross-section of the grain, the flux from the star, and the speed of light. Okay, now, for a black body, we're going to have, well, that's weird. So we've got the flux is given by sigma t to the 4, and so for the sun, we've got phi is given by the radius of the sun, the temperature of the sun, the distance from the sun, and sigma t to the 4. So remember that this is, basically it would be sigma t to the 4 if we were just at the surface of the sun, but when we want to get it at some distance, that light is always going out through a surface at some distance from the sun, so we should get that equation. And so we're going to, we've got this radiation pressure that's given by the cross-section, the flux, etc. And now I'm just going to plug in the A. I'm going to assume that my particles are spherical, so they have a cross-sectional area of pi r squared. It's a good approximation. And then I can put in my radius, sigma t to the 4, my c and d squared here. And so this is, r is the radius of the grain, r sun is the radius of the sun, t sun is the temperature of the sun, d is the distance from the sun, and so this is the force that a given grain will feel, and clearly it is dependent on distance squared. Now what really matters is the relative force on the grain. So we have a gravitational force, which is given by g m sun over the mass of the particle, which is, again, we're assuming a sphere, 4 pi r cubed over 3 times the density, and we've got to equate these. So basically, when is the radiation pressure going to overcome gravity? So all I've done is to divide one by the other and rearrange them, and so there's just some simple algebra. And if we actually plug in numbers, and this is in SI units, and so what I've done is to plug in the value for sigma and C and m son and g and so on. The only variables are the size of the grain and the density of the grain. So let's put in some reasonable numbers. Well, the grains range from, icy, so there might be 1,000, up to things that were in the center of an asteroid that's been destroyed, and so you get iron grains, and so they can be in this sort of range. So we can then work out, though, what if this number equals 1? At what point does the radiation pressure compete with gravity? And so we just make this equal to 1, rearrange, we get R equals this, and so what you get is approximately, that R is 1 micron. So for grains smaller than a micron, what this means is that the radiation pressure pushes more effectively than the gravity holds it in. So all grains smaller than this size, and remember this is density dependent, so some bigger ones will get pushed out. They will achieve escape velocity by being accelerated by the photons. So that's got rid of the very small grains, but what about bigger grains? Well, we have the Poynting-Robertson effect. And this works for larger particles where gravity is winning, but we still have radiation pressure. And so basically particles that are orbiting the sun see the sun's light coming from just in front of them. This is similar to the aberration of starlight, that it takes time for light to get from the sun to the place where the grain is. And so from the velocity of the grain makes it look like it's coming from just in front of it instead of tangentially, so that it's actually impeding their progress. So what you get is it's pushing on the grains and it's pushing them backwards. It's not going to push them backwards far enough to push them out of the system, but it retards the motion. It slows them down. And if it slows them down, it will eventually end up without circular velocity. Remember, if it doesn't have circular velocity, it will no longer fall around the sun, it will fall into the sun. And so it spirals into the sun. And we're not going to derive it. This is actually obviously distance dependent, because that affects the number of photons that you will have hitting you and slowing you down. But asteroids larger than about a foot will not really be affected by this. But at the Kuiper belt, it's actually a much smaller thing. So things as small as a few millimeters can still survive in the Kuiper belt, whereas at the asteroid belt, something as small as a few millimeters will be retarded and allowed to fall into the sun. And so here's a way of thinking about it. So again, we've got the speed v of a particle, it's in orbit, and it makes an angle between the radiation and the radius vector, that is the direction directly to the sun, which is theta equals v upon c. Again, look back at the aberration stuff. So the component of the radiation force that impedes the motion is basically v upon c times the radiation force. Remember that when you have very small angles, you can approximate in radians the angle, the tan of the angle to the angle, or the sine of the angle to the angle. So that's where that comes from. The particle is originally at distance d, and so you can come up with this, I'm not going to derive it, that the time in years for it to fall into the sun is given by this factor times the density, the radius, and the original distance squared. And so you can put in some numbers. So if you've got an asteroid that is a distance of 2.5 AU and has, a rocky density, and you can't actually see that very well, but the age of the solar system is about 4.5 billion years, and so up to about 1/3 of a meter, things will have had time to spiral into the sun. Whereas for a Kuiper belt object at 40 AU and a much lower density, the time for the age of the solar system is about 4 millimeters, and so those things will have fallen into the sun. And so just to summarize this, we have small particles less than about a tenth of a micron will be pushed out of the solar system directly by radiation pressure, and larger particles up to about a foot across will effectively spiral in, and so we get rid of the dust. And we get more dust made all the time, and this is actually also an important factor with things like the rings around Saturn, Jupiter, etc. And they get cleared out even more. And so just to summarize the formation of the solar system, we have a gas and dust cloud that collapses. The dynamics give rise to a disk. The chemistry gives you the condensation sequence, which explains the difference between terrestrial and Jovian planets, both in composition and mass. So we have accretion of rocky bodies for both, but then you get collapse of denser bits of gas to make Jovian planets and their moon systems. And then the clearing out is what happens last.